Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining, on anode shape prediction and tool design for ECM and ECMM. This is part 2. Sorry. Organization of the talk is following: introduction to tooling design for ECM and ECMM, anode shape prediction in ECM and ECMM, other approaches for anode shape prediction in ECM and ECMM, what is correction factor method of tool design in ECMM, finite element method for the anode shape prediction and tool design in ECM and ECMM, conclusions, and then references. Now, while some part of this we have already discussed in part 1, it is assumed that you have already studied the lecture on electrochemical micromachining, because I am not going to deal with the theory of ECM and ECMM. References mainly anode shape prediction and tool design for ECM process, published book on advanced machining processes. Reddy et al. Published a very interesting and useful research paper on tool design for ECM correction factor method. Most of the part in this particular lecture is taken from this particular paper published in ASME Transaction, Journal of Engineering for Industry. This is volume 110, published in the year 1988. And then there is another paper published on anode shape prediction in through mass electrochemical micromachining using finite element method. It was published in Machining Science and Technology. And Vijay Bhattacharya published a paper on International Journal of Machine Tool and Manufacture in the year 2000. What we have done in part 1 lecture on tool design: introduction to tooling design for ECM and ECMM, anode shape prediction in ECM and ECMM, various approaches including cos theta method, numerical approach including finite element method, finite difference method, complex variable approach, nomographic approach, etc. Then tooling design methods including cos theta, complex variable, FEM, FDM, correction factor method, etc. Introduction was given. Flowchart for anode shape prediction used in numerical methods, analysis of some of the methods, and other approaches for anode shape prediction in ECM and ECMM. So the first part mainly dealt with anode shape prediction in ECM and ECMM. In part 2, correction factor method in detail will be discussed. It can be applied for various shapes of the component, but I am just dealing with very simple case of flat workpieces. Tool design in ECM and ECMM. Tool design in ECM using finite element method for 1D and 2D. Some introduction is given to this part also. Comparison of theoretical and experimental results. At IIT Kanpur, we had developed this particular method first time, long back, maybe 3 decades, 4 decades back, and published it. And here are some results before I really discuss in detail. It will tell you how accurate it is. Here you can see this is the design tool, this dash line, and then you have the X, another one is the experimental results of the anode shape. These are the experimental results. Here also you have the experimental results of the anode shape, and then you have the predicted anode shape, and both of them are overlapping with each other here as well as in this particular case also. And then you have the use tool. So we use this straight sided this tool, and this was the design tool. So you can see the differences at here as well as here, but both are giving exactly more or less exactly the same anode shape. See the difference between the design and the use tool, and then you have the predicted work shape and obtained work shape. Both are overlapping with each other. This is taken from the paper by Reddy et al. Details of correction factor method for cathode design. This is what today we are going to discuss. Correction factor concept has been applied to modify in different stages or different steps tool shape assumed in the first design cycle, tool design cycle. The modification continues till it produces the desired work shape or anode shape within the specified tolerances while machining under given machining conditions. The procedure of designing a tool is summarized below. Step 1. The anode profile is estimated using anode shape prediction method using an assumed or modified tool shape and specified machining condition. Then step 2, compare the estimated and desired anode profile, because you require certain shape and size of the workpiece final. So whatever is predicted theoretically, you compare these two, and which I have shown you in the earlier slide, that comparison was very, very close to each other. We were not able to even see any difference between the two, and obtain the deviation or error between them whatsoever is there. If the deviation is more than the specified tolerances, this is important, then calculate the correction factor. Modify the tool shape by applying the correction factor. Procedure will be discussed in detail. And then repeat step 1 to 4. This is step 4 till the desired tool shape is obtained. Flow chart is shown in the next slide. Now desired tool shape will be told to be obtained at the point when the difference between the obtained workpiece surface and the required workpiece surface is less than the tolerances that have been prescribed on the component itself. So some schematic flow chart is given here. What steps are to be followed in correction factor method? First one is start the process. Assume the initial tool shape. There are certain points which have to be taken care of while assuming the initial tool shape. Then predict the work shape. This, how to predict it, we have already discussed in part 1 of anode shape prediction. Then compare the computed work shape with the required work shape and obtain the deviation between the two. Then calculate the error at each node. Is error greater than tolerances? Compare for all nodes. There are different nodes. If yes, calculate correction factor and modify the tool shape. If, and then go to the step 1, this particular predict the work shape. Whatever is the modified tool, with that compute the work shape or the anode shape and compare it, predict it, and then follow the other steps. Definitely this step and then this step. If no, if error is not more than the tolerances for all nodes, please note it clearly written, compare for all nodes, and if says no, then stop the process and you continue till you reach the stop the process. Correction factor method for cathode design or tool design. Computational details of the correction factor method are discussed later for electrochemical plain parallel electrodes machining and electrochemical drilling. Due to the shortage of time, I will not discuss this electrochemical drilling. I will discuss only the plain surfaces, plain parallel electrodes. The tool design procedure is completed in a number of design cycles, and in each design cycle the tool profile is modified partially. Then each design cycle is made up of NC number of cycles. This number is such that the total time of machining, NC into delta T, is sufficient to produce approximately, I have written deliberately the approximately because tolerances are also always there, so it has to be within the tolerances. Approximately the desired shape and size of the anode, that is the workpiece. And you can calculate the number of cycles NC is equal to V divided by delta T into MRRV. Now here V is the total volume of work material to be removed, delta T is the machining cycle time, and MRRV is the volumetric material removal rate. So you can get number of cycles for which machining or theoretical machining or computational machining has to be performed. The design procedure for first and second design cycles is different from the third and subsequent cycles. Tool design cycles for flat workpieces. Tool shape. The tools for the following 4 types of work shapes have been designed and discussed elsewhere. In the research papers they have been discussed, in the thesis of Mr. Reddy they have been discussed. Here I will just discuss for one case only. Straight line, y equal to a plus bx, exponential y equal to a plus b e raised to power cx, parabolic pi is equal to a plus bx plus cx square, and non-standard shape. They have been designed, but I am just going to discuss only the one. The tool shape in the first design cycle has been assumed as complementary to the desired work shape. Assuming the initial work shape to be flat, the inter-electrode gap calculated for different nodes is shown in the next slide. Tool design for flat workpieces continues. Please see it carefully. The tool shape in the first design cycle, this has been, because see, this is the required work shape. This is the required work shape, and this is the assumed tool shape for the first design cycle. So you can see the gap between the two is kept more or less the same, and based on the workpiece shape the tool has been assumed. This gap is the same as this gap over here, initial first stage cycle. Now these are the different nodes, 1, 2, 3, 4, these are the different nodes. Electrolyte is flowing over here, and this is the required work shape, and this is the initial work shape. Initial work is here, this is the initial inter-electrode gap. Assume tool shape and initial work shape before electrochemical machining starts, because this is the computational work, so you have to assume both. First tool design cycle continues. Now here machined work shape in ith cycle A1 B1. Here you can see here, this is the A1, this is the B1, and I plus 1th cycle A2 B2, and you have the A2 and B2. Now I plus 1th cycle, machining cycle is broken into 20 sub cycles, each of 1 second. Delta t becomes equal to 1 second. Computational machining cycle time delta t is chosen as 20 seconds. With this of delta t, the total amount of material removed in NC cycles, we have calculated it already, from the workpiece may be either more, like A2, B2, EF, that is there, this is more, or less, A1, B1, this is less 1, A1, B1, EF in the IS cycle. So, IS cycle and I1 S cycle. Then the desired one is the ABEF, that is the required one or the desired one surface of the workpiece. In order to reduce the difference between the desired ABEF and the predicted A2, B2, EF amount of work material removed, the value of delta t in the computational cycle is decreased to 1 second, because this is either high or low because of the difference in one cycle. So, what you can do, you can divide this 20-second cycle into 20 cycles each of 1 second. Let the machining be stopped within I plus 1th computational cycle, say 10th subcycle, shifting A2 B2 to A3 B3. This is A2 B2 to A3 B3. This moves from here to A3 B3 over here, such that at node A3 minus A is less than or equal to Tz, that is the tolerance. If it is less than tolerance, then it is okay. Where Tz is the specified tolerance limit. That means here this indicates that the difference between the required shape and the obtained shape is less than tolerance. Tolerance is provided, then you can accept this particular workpiece shape. Let the difference at node 1 be called as AR1, and then AR1 is equal to by R1 minus by C1, where 1 is the cycle, R is the required one, C is the compute. This is given. 1 indicates the node number, 1 indicates the node number, not the cycle, node number, R indicates required, and C indicates computed. To calculate the error at different nodes, say 2, 3, etc., superimpose point A3 to A. See in the previous figures, A3 to A, you can see here, A3, this A3 to point A, this point, you can see here, this point is to be superimposed here with A. Superimpose point A3 on A, the error at any point can be calculated as follows, because at A3 and A, since they are superimposing, so their error becomes 0, they are overlapping. If the error is positive, in the following equation, add it to tool coordinates, because tool coordinates have to be modified for the next cycle, design cycle, and vice versa. I is the ith node number. So, ERI, that is error ith node number, by RI minus by CI minus AR1, right? Whatever was the error there, we have seen over here, AR1. So, that is to be substituted here. So, you can see, because these two are matching here, A3 and A, for which we calculate over there, and this is the error, this is B3 and this is B. So, workpiece is there, you have the required workpiece, required one here, this is the error, this is the computed workpiece. So, you can calculate the error at different nodes, and if it is positive, add it to the tool node on that particular point, or negative, then subtract it. Error between required and predicted shape. Electrochemical plane parallel machining after superimposing A and A3. This is superimposing A and A3 and this is the error. Second cycle tool design. First cycle tool design is here. This is the second cycle tool design, so that you get the predicted and the required workpiece shape closure as compared to the first cycle tool design. Second tool design cycle for flat workpiece, using the errors calculated at the end of the first design cycle. The correction factor for each node has been calculated. CF indicates correction factor for ith node, ERI. Using this correction factor, the tool shape is modified before computational machining. That is computation of inter-electrode gap, electrolyte conductivity, electrolyte temperature, etc. This should be small k. Electrolyte conductivity is indicated by small k. It starts in the second design cycle to obtain tool shape and size for the second design cycle. The values of the above calculated correction factor are added or subtracted to by coordinates of that node of the tool, of that node, this is very important, of the tool used in the first design cycle. Third and subsequent tool design cycles, anode profile in the third design cycle is computed using the tool shape modified at the end of the second design cycle. After estimating the errors or after calculating the errors, the correction factors are calculated as given below for the nodes to be modified. For third and subsequent design cycles, the procedure for calculation of the correction factor remains the same. To calculate the correction factor CF, the ratio of difference in inter-electrode gap to the difference in errors ER we calculated in the previous M-1 and present M cycle, tool design cycle, is assumed to be equal to the ratio of difference in inter-electrode gap to the difference in errors in the present and the next cycle, that is M and M plus 1. So, this is important equation by M minus 1 I minus by M I divided by ERM minus 1 I minus ERI equal to by M I minus by M plus 1 I over ERM I minus ERM plus 1. This equation is used to and used later on also for zero error in the next cycle, that is M plus 1th cycle, because at present we are at mth cycle. This error we assume theoretically to be 0. So, CF M plus 1 cycle minus by M minus 1 I plus by M I over ERM minus 1 I minus ERM I into ERM, where by M plus 1 I is equal to by M I plus CF M plus 1 I. For M greater than 2, we have already mentioned that after second design cycle, the procedure remains the same for all cycles. In case of electrochemical drilling, all the nodes are active throughout the machining time. After each computational machining time, one additional node becomes active because it is moving downward. Once it is moving downward, then depth keeps on increasing. That means you are increasing additional node or nodes in the machining zone. Further, there is nothing like equilibrium gap in the side zone during electrochemical drilling. This we have already seen while discussing electrochemical micromachining and electrochemical micro drilling. Hence, inter-electrode gap is continuously increasing in the side gap. That is what this is there. Here is the tool, and this is the side. It is telling, because this portion like this, sorry, side gap. This is in the IMS cycle. This will become like this, because continuously material is being removed in this direction. So in the next cycle it becomes like this. Therefore, correction factor for M plus 1th cycle during electrochemical drilling is calculated as follows. However, we are not going to discuss in detail this drilling operation, but this is what this equation can give you, the correction factor method. For zero error in the next cycle, that is M plus 1th cycle, this is being assumed theoretically. CF M plus 1I is equal to CF M I minus CF M minus 1I minus CF M I. You have to multiply whole of this part for M greater than 2, that means third and subsequent cycles. But for M less than or equal to 2, we have already seen this. Sorry, this is coming reverse, I don't know why. This is like, and then correction factor is equal to 0 for ith cycle. This is nothing but ER1I, ER2. Now please see it. This is the detailed flow chart for following this tool design for plane parallel electrodes micromachining. You start the process, read the given data. Here you will have the material properties, tool design, tool material properties, machining conditions, etc. Read the required work shape parameters. What is the shape of the workpiece that you are going to machine? Compute tool shape for first cycle. These all will be in the form of the subroutines. You have to make subroutine for each one of them. Compute inter-electrode gap IEG and Y coordinates of RWS rows. Compute number of computational cycles. Generate coefficient of stiffness matrix, because this is for using finite element method. So stiffness matrix is to be generated. I will give some details about this later on. Compute electrolyte velocity, electrolyte flow velocity. Compute HE and apply boundary conditions. Some details I will give you later. Solve simultaneous equations for unknown nodal temperature. Some subroutine is there, GET. Then if I void, that is void fraction, is equal to 1, yes, compute void fraction. No, then modify temperature modify temperature accounting heat transfer to electrodes. There is another subroutine, HTA. Then compute electrolyte conductivity, modify computational cycle time, compute feed rate. Now if ISEQ equal to 1, yes, compute IEG with suggested equation. If no, compute IEG with implicit equation, and then compute current density, estimate DOM and OWS, and if DOM is greater than or equal to RD, all these subscripts are defined in that paper also. Yes, then if no, then you go to this particular point over here. That is what is shown over here. From here you have to come like this and come over here. If yes, then you continue further, then compute error or deviation between the RWS and OWS, and then KMME equal to 1, and then you come down. If KMME yes, 0 this way. If no, then come here and then move in the next one, that you can see here. If error less than accuracy required or tolerances, yes, and then you go up. If no, then make this as 0 and MC is equal to 1, yes, then correction factor is equal to error, and you come over here. If no, compute correction factor for IS no, and then come here modify tool shape and inter-electrode gap. Then if I is equal to NN num, then you can increase this I by 1 and go up. If yes, then if IKMME is equal to 1, yes, print results and draw design tool shape, then stop and end. So flow chart for cathode design for electrochemical plane parallel electrode machining operation. This is not, this is a detailed flow chart, but some of the steps they are hidden and you can refer them in the research paper or the thesis, MTech thesis of Mr. Reddy, available on the site of IIT Kanpur. But papers deal all the details, that is published in Transaction ASME Journal of Engineering for Manufacturing. Finite element method for anode shape production has been applied, and tool design for in ECM also has been applied. Now in this finite element analysis, discretization of the domain into set of finite elements, weak formulation by Galerkin method, derivation of the interpolation function, development of finite element method model, imposition of boundary conditions, calculation of the secondary variables. There are certain assumptions which are made while deriving or while conducting finite element analysis. Electrolyte flow rate between the two electrodes is high enough to neglect changes in electrical conductivity of electrolyte. Workpiece material is homogeneous. Reaction products do not affect electrolyte properties. When I am saying workpiece material is homogeneous, that simply means it is applicable for pure metals. You may have to make the changes if you are dealing with alloys. Electrical field in the gap is quasi-stationary. Workpiece, or that is anode surface, is uniformly covered by electrolyte, and primary distribution of electrical potential in the gap, that is electrode polarization, is constant and is taken as an average value. Now let us discuss selection of the variables for this particular work. Primary variable is the potential, secondary variable current density, source variable electric field, anode, and we can say del 2 phi is equal to 0 at the anode, del 2 phi is equal to del 2 phi over del n equal to 0 on the boundary. This is there, anode is there, and del phi over del n here on the boundary, here on the boundary. This is the inside the inter-electrode gap, and here is the cathode. So inside the inter-electrode gap, this is the inter-electrode del 2 phi over 0. At the boundary, you have del phi over del n, and del phi over del n is equal to 0. Now this is for the finite element method, 3-dimensional. You can see here, this is the anode, this is the cathode, and between the two you have the inter-electrode gap. And here at the boundary you have del phi over del n is equal to 0, del phi over del n is equal to 0, and here at the anode shape del phi is equal to u, some potential being applied, and del phi over del n is equal to vi cos theta over zeta omega k, and all those things are given there. You can see over here Vf kV over k cos theta at anode boundary, and phi is equal to phi a is equal to u on anode boundary, anode surface, and phi c is equal to 0 at cathode boundary, where Vf is the feed rate, kV is the electrochemical equivalent, k is the electrolyte conductivity, this is the small k, this is the capital K, theta is the angle between normal to the anode and feed direction of the cathode. This is for 3D, but you can do it for 2D also, which is much simpler than 3-dimensional. This was performed by Lee. Mathematical model for anode shape prediction, we have seen it while discussing in part 1, del 2 phi over del x2 plus del 2 phi over del y2 is equal to 0. This is by 2 is equal to 0, where phi is the potential function varies in each node. Dirichlet essential boundary condition, and here you have the at the cathode, this is for at the anode, where f star j and g star j, they are here given over here, are the arbitrary function of the cathode and anode over potential, because potential that you are applying is V, but over potential is there. So effective potential really becomes V minus over potential. This comes as over potential over here. Newman boundary condition is there, del phi over del n, where at the boundaries I have already shown you in the earlier figure. Interpolation function, phi is equal to summation I equal to 1 to n number of the node, ni x y phi I. So ni is the interpolation or shape function which varies as follows: ni is equal to ai plus bi x plus ci y, where ai is this much xj yk minus xk yj over 2a, same way bi and same way ci. So you can calculate ai bi ci over here theoretically, and these are the I, j and k nodes are there, triangular elements are assumed. This is very important to assume appropriate 2D or 3D or 1D element, because shape of the element and function of the element makes a difference in the computed anode shape. The field vector can be found by minimizing the function I phi and satisfying the boundary conditions. I phi equal to 1 by 2 del phi over del x whole square plus del phi over del y whole square dx dy, and kij in here del ni over del x into del nj over del y plus del ni over del y into del nj over del x dx dy. So this is how you can do it at the cathode, at the anode, and you have the inter-electrode gap. Del phi over del n is equal to 0 as the boundary condition, and this is another meshing elements, and here you can see these triangular elements are chosen, but as I have told you, you can have different shapes of the element depending upon your requirements. These are the stiffness matrices. You can calculate the stiffness matrices using these particular equations. Calculation of the secondary variables, j k is equal to ke del phi over del n. Ke is the electrolyte conductivity, small ke. J is the current density. This is the current density. This should be capital J, but you can take it like this. J current density normal to the workpiece surface, and n is the unit normal to the workpiece that is given here. Variation of electrolyte conductivity with temperature. This is very important equation. Normally the books and the papers you get Ke equal to K0 1 minus alpha g raised to power m into 1 plus delta or lambda rather T minus T0. You can see here this is the white fraction taken into consideration. This is the initial electrolyte conductivity. This is the effect of the white gas bubbles or white fraction, and this is the effect of the temperature, because temperature of the electrolyte is changing continually. But this is not enough. Normally people are using this particular equation and they don't get the satisfactory result. So at IIT Kanpur, one of the students developed this new equation, and where he said sludge formation is there during electrochemical machining and electrochemical micromachining. So he suggested that you multiply this equation by x, multiply by 1 plus alpha m raised to power m, where is the m is the fraction of the sludge in the electrolyte, and n is the exponent. So you have to calculate what is the value of alpha m, it may, please note it carefully, it may increase the conductivity, it may decrease the conductivity depending upon the sludge that is being formed. So this plus is not always plus, this may be plus or this may be minus also in certain cases. And if you are using this particular equation for the calculation of conductivity of the electrolyte, you get better results. Where 0 subscript denotes the condition at the entrance of the inter-electrode gap, that is K0 is the initial initial conductivity of the electrolyte. Y conductance constant and T electrolyte temperature. M is taken as 1.75 here, but all this depends upon, you can calculate this or find out with the help of the experimental results. Same way you have to also find out the value of N over here. Here is the M exponent, here is the N exponent. And this lambda, this is conductance constant, this is available in the handbooks or the tables are given over there. This is nothing but this lambda. For one dimension void fraction defined as alpha g, Gg over G, because we are calculating alpha g over here, void fraction over here. So Gg denotes the volume of inter-electrode gap occupied by the gas. This you have to theoretically also you can find out with the help of the chemical reactions or electrochemical reactions. This alpha g can be evaluated. The temperature rise of the electrolyte can be computed from dt over dx, J square, K, small k, B, rho E, C. This is the J is the current density that I have shown to you. This should be the capital J. And here the effect of sludge present in the electrolyte on the electrolyte conductivity has not been considered. When only this equation was given up to this T0, then it was not considered. To account for this, above equation should be modified. Above equation for K multiplied by 1 plus alpha m raised to power n, that is multiplication over here, where alpha m is the sludge fraction and n is the exponent. I have already explained this. Stages for the finite element method for the tool design for ECMM. Tooling design for ECMM finite element approach. Stage 1, any significant change in theory of ECM. Stage 2, understanding and development of correction factor method for tool design in ECMM. Stage 3, finite element modeling of electrochemical micromachining, which includes primary variables, secondary variables, size of element, shape. These two are very important parameters to be selected carefully. Size of the elements, because all this will decide with what accuracy you are going to get the computed results or predicted results. And shape of functions, that is also, shape of the elements is also very important, I have shown you. And calculation of secondary variables, anode shape prediction. Stage 4, stage 5, validation of theoretical model by the experimental data. This is another very important step, because you must always compare your theoretical or computed results with the experimental results and find the deviation. If deviation is more than 5% or even 10%, then you should rethink and remodel the process, because there is something wrong. Too many assumptions, too many simplified assumptions have been made. So relax those assumptions to make theoretical results closer to the experimental results. Stage 6, tool design, calculate correction factor, apply for each node of tool, perform operation, recompare the obtained and the required anode shape and modify the tool. Stage 7, continue till error obtained, means keep modifying the tool shape and size till error obtained is less than the tolerances specified for each node on the workpiece. Then you can stop. So these are the different steps to be followed while applying finite element method for tool design for electrochemical micromachining. What we have done in this lecture? What is correction factor method of tool design in ECMM? What are the steps involved in correction factor method? How to apply correction factor for plane parallel? This is plane parallel, not R, this is L. Plane parallel micromachining and microdrilling. We have not discussed microdrilling as I mentioned you in the beginning because of shortage of time. You can see it in the paper or the thesis. Finite element method for the anode shape prediction and tool design in ECM and ECMM using correction factor method has been discussed with reasonable details. Just a minute, this is not there. ECMM. Then conclusions. At the end of it can be concluded that anode shape prediction and tool design for ECMM operations can be done using the correction factor method. These are the references. I have given you most of the references over here, except that Reddy's paper is not mentioned somehow, which is most important. So you can refer it, you can see it. Thank you very much. Thank you.